Hello everyone, welcome to the Makri Virtual. Hope you are doing good. Today I'm going to continue with chapter number 5, that is optimizing program performance. Till now we have covered 4 to 5 topics or 7 topics. Now I'm going to start with the 8th topic, that is loop unrolling. This is a chapter that denotes how to optimize or how to increase the program performance or the performance of the program and increases the efficiency of the program of the computer. So I'm going to start with the previous feedback or the previous recap of the previous class, that is your yesterday's class. So let's take a quick recap of the previous class. In the last class we have discussed about the data hazard, how it will be overcome, and how different understanding the modern processor, how modern processor will understand with each other. This is understanding the modern processor. So yesterday topics was there are 2 topics. First one is your understanding the modern processors. We have discussed about the purpose of the CPU, what is CPU, what is the functionality of the CPU, how CPU are recognized or how CPU features are recognized, like clock speed, cache size, number of cores that affects their performance. Then CPU, it is the brain of the computer system. Why it is known as brain? Because every operation, every task is performed by the CPU. That's why it is known as the brain of the computer system. The purpose of the CPU is to carry out program instructions, that is known as instruction set. CPU is also known as the microprocessor. So this is the diagram for the CPU. There are multiple pins available that is attached to the CPU, that is also known as microprocessor. Then what are the elements or what are the components of the CPU? It depends on the designing of computer. But there are some common features that is available in every CPU, whether they may design in other format or different format. The common features or the common components are electronic clock, control unit, instruction unit, ALU, FPU, registers, buses, bus management unit. And what are the CPU components? Now let's discuss one by one. Clock, that is used to carry out or the rate at which CPU runs and synchronizes the various components. The higher the clock speed, the more instructions the CPU can execute. And the speed of the clock is measured in megahertz. Then control unit, it is the nervous system that controls or performs the task of controlling, that is fetching the instruction, decoding, managing. It also contains various registers such as program counter, program instructions, current instruction register. Then next is your instruction unit, that consists of ALU, addition, subtraction, logical operations, FPU, which performs the mathematical functions on the floating point numbers, registers. Then buses. Buses are the wires that is used to carry the information, or that is used to carry the information or data from one place to the another place, or from one component to the another component of the CPU, as well as with the external devices, as well as internal devices, internal memory, that is your RAM. There are 3 types of buses available in computers, that is address buses, data buses, and control buses. And the bus management system is used to transfer the data for management, for transfer, that includes the linking to the RAM also. This is the diagram that shows the various components of the CPU. There are 2 types of buses used. One is internal buses, one is external buses. Internal is used for internal level, that is within the CPU only. External buses are used for the external devices like pen drive, your CD-ROM, floppy disk, that is used for that is linking is done by the external devices. Then these are the multiple functionality. These are the cache memory, instruction cache, memory controller. Then what are the functions of the CPU? First function is your fetch, that is retrieving the information. This is the first step. Then decode, that is it identifying the opcode. Opcode means the operation, or the opcode is the variable on which operation is to be performed. That is your opcode. Then next function is execute state, that interact with the CPU, that interact with the ALU control unit to execute the instructions. Then next is your CPU characteristics versus performance. Means what are the difference between, or what is the comparison between the characteristics and the performance. One is your clock speed, that is your speed or rate at which data will be transferred from one place to the another place. This is the speed of the processor is measured in the clock speed and measured in the terms of megahertz. This is your clock cycle, that is high, low. This is the summary. The higher the clock speed, the more instructions the CPU can execute per second, resulting in a faster running computer system. Next, cache memory or cache size, that is used for the cache memory. This is the cache memory that lies between the CPU and the main memory, that is your RAM. A CPU with a larger cache memory and more levels of cache memory will have a high performance than one without the cache memory. Number of cores, that is the number of processor used. For example, if I am using the client server architecture, there are 5 systems, so we are using 5 processors that are known as the cores, that is known as or independent actual processors. A dual core processor contains 2 cores and a quad core processor contains 4 cores. Suppose I am saying it is a dual core processor, that means there are 2 cores or there are 2 processors that is available in the core. The biggest performance gain when using a multi-core processor is when the software has been specifically written to run the multiple cores. Summary, a multi-core CPU will have a high performance than a single-core CPU. With the same clock speed, same resources, everything is same. Next topic which we will discuss with in the last class is abstract model of processor operation. That is, what is the architecture of the processor, that is known as the abstract model of the processor. There are multiple computer system components like hardware, operating system, application, programs, user. Hardware is the element that can be touched, that is tangible in nature, that provides basic computing resources like CPU, memory, input-output devices. Next is your operating system that provides the interface between the user and the hardware. Then application program that defines the way in which system resources are used to solve the problem. For example, if I am talking about the MS Office, that is your application program. Then users are like we are the end users, example machines, program, computers. Then this is the abstract view of the system. That is, OS is the mediator or interface between the user and the hardware. There is a user at the starting phase. There are so many users and number of users. Then there is an application program like compiler, assembler. Then there is an operating system that provides an interface between the hardware, this is the hardware, and the user. Then what security goals does operating system provide? That is, what are the security goals that is available or that is provided by the operating system? Goal 1 is enabling multiple users securely share a computer. That is, more than one computer or more than one user are sharing the computer at the same time in a secure manner. Then what is CIA? That is confidentiality, integrity, availability. Goal 2 is ensure secure operation. First one is your secure network. Now, secure operation in a network environment. Security is about controlled sharing that ensures separation between physical, temporal, logical, cryptographical. Then access control to the memory. CPU modes, that is also known as the processor mode or the privileges. There are 2 types of modes, that is system mode and the administrator mode. System mode does not have a full facility, full authority, but the administrator mode have a full authority, full privilege. So system mode can execute any instruction, execute any memory location, can enable and disable interrupt. Then system mode is same as the administrator mode. This is also known as the Privilege mode, master mode, supervisor mode, kernel mode. Next mode is your user mode, that is used by the user. They don't have a privilege or they don't have access to the multiple processor. So system mode means that is accessible or that have a full privilege. But user mode does not have a full privilege, that can be used by multiple persons. Then if I am going to convert or translate or transit from one mode to the another, that is user mode to the system mode, that can be done using the gate known as the system call. Now what is the system call? That guide gates from user mode to the kernel mode. Now what is the difference? This is the difference we have discussed. This is the diagram we have discussed. There is a kernel, there are multiple processors. Kernel lies between the processes and the hardware. That's all for yesterday's session. Now let's start with the new session, that is today's session. Today's first topic is loop unrolling. These are the 4 topics which we have to discuss in the today's class. Now, next is your loop unrolling. It is a program transformation that reduces the number of iterations for a loop by increasing the number of elements computed on each iteration. It says it is a program transformation, that is transforming the program from one place to another, that reduces the number of iterations. How it reduces? By transforming the program from one part to the another part. To reduce the number of iterations, number of looping for a loop by increasing the number of elements, means increase number of elements increases the number of variables that is computed on each iteration. That is a loop unrolling. So it reduces the number of iterations by increasing the number of elements. These are the examples. Now let's see with the help of PPTs. So today's topic is chapter number 5, that is optimizing the program performance continued. And there are 4 topics that we have to cover in this class only. First is introduction, then pipelining as I told you earlier, then level parallelism and optimization or dependency, then loops, that is loop unrolling. So first of all, what is the scheduling? It is the ordering of program execution. That is, if I am writing the program, if I am executing the program one by one, that is known as the scheduling. So it is the process of ordering the program execution so as to improve the performance without affecting program or correctness, or without affecting program correctness. That is, it is the ordering of the program that can be executed by the CPU. Our focus to date has been on hardware-based scheduling, which involves execution scheduling or rearrangement of issued instructions to reduce execution time. Then this says, today we will look at the compile time or compile-based scheduling, which is also known as static scheduling, if the hardware does not subsequently reorder the instruction sequence produced by the compiler. Then how does software-based scheduling differ from the hardware-based scheduling? Unlike, that is not the same as the hardware-based scheduling, the overhead due to intensive analysis of the instruction sequence is generally not an issue. We can afford to perform more detailed analysis of the instruction sequence. We can generate more information about the instruction sequence or instruction sequence. Still, we can assess the hardware during the compile time by exposing more ILPs in the instruction sequence or performing some classic optimization. Now, what is the architecture of a typical optimizing compiler? First one is your front end. This is your front end that is available to the user, that is seen by the user. Then there is a middle end, that is the mediator of the front end and the back end. Then there is a back end that lies at the back end. The user cannot see the back end part. This is your FE, back end, or sorry, not back end, it is front end. This is the high level language, example Pascal, C, Fortran, that checks syntax and semantics. Then there is a middle end, that is your mediator. There are 4 number of inputs, that is O1, O2, On-1, On, intermediate representation, example AST, 3 address code, DAG, that performs local optimization and performs global optimization. Then there is a backend, that is at the backend stage, that is your machine language, that is at the machine language. Amid the target architecture machine code. Next, compile type optimization are subject to many predictable and unpredictable factors. These are the multiple factors that affect the optimization at the compile time. What are some typical optimization? As I told you, there are 2 types of optimization: high level optimization and low level optimization. High level optimization says it performs high level optimizations that are very likely to improve performance but do not generally depend on the target architecture. Means that performs a high level optimization but does not improve, or likely to improve the performance but does not depend on the target architecture. Example, scalar representation or scalar replacement of the aggregates, data cache, that is using the cache memory optimization, procedure integration, constant propagation, symbolic substitution. Then next part is your low level optimization that performs a series of optimizations which are usually very target architecture specific or very low level. Example, software pipelining, loop unrolling. So today I am focused on these topics, that is your loop unrolling, software pipelining, and the multiple parallelism, that is we are using the same architecture at the multiple points. This is what I am going to talk about. So this is what is I am going to talk about today. So this is done. Introduction is done. Now next part is your basic pipeline schedule. This says basic pipeline scheduling techniques involve static prediction of branches, usually without the extensive analysis at the compile time. That is, without using so much analysis at the compile time, basic pipeline scheduling involves the static prediction of the branches. Static prediction methods are based on the expected or observed behavior at the branch point. Usually, these are based on the heuristic assumption, that is assumption we have taken, that is based on the assumptions. Key idea is that hope that our assumption is correct. If yes, we have gained a performance improvement, otherwise we are in a loss, or we are going to waste a clock cycle. These are 2 approaches for prediction. One is direction based, one is profile based. Now, what is direction based? How we can assume branch behavior is highly predictable at compile time. Perform scheduling by predicting branch statically as either taken or not taken. That is, we assume that scheduling is done statically, can either taken or not taken. Assume the branch behavior that is predictable at the compile time. Alternatively, use forward-going approaches as not done, not taken, and backward-going branches as taken. That is, exploit the loop behavior. Example, filling a branch delay slot, a code sequence, and needs flow graph, that is at right. This is LD, DSU, BU. These are the registers. BEQ, Z. These are also registers. OR operation, that is using the registers R4, R5, R6. Then using the sequence or using the flow, this is the flow, that is R1 is not equals to 0. Use the OR operation, use the DADDU operation. This is DSU, DU, this is this one, and BEQZ are output dependent on the LD. Next is your profile-based prediction. That is how profile-based prediction can be done. First of all, it says collect the profile information at the runtime. Since branches tends to be bimodal, that is highly biased, a more accurate prediction can be made based on the collected information. This produces an average of 15% of mispredicted branches with a lower standard deviation, which is better than the direction-based prediction. This might involve profile collection, compilation, or runtime, which might not be desirable. Sorry. So this is the profile-based prediction. Now we have done with the pipelining scheduling. There are two types of scheduling. One is profile-based, and another one is your direction-based prediction. So we assume on the prediction, we decide on the prediction. We are using the approaches, that is which pipelining can be used at the static time or the runtime. Now, next is your instruction level parallelism and dependencies. That is how to instruct the level or how to use a multiple level parallelism and the dependency. This is very important topic. This is known as ILP, that is instruction level parallelism. That means inherent, that is inherited the property of a sequence of instructions, as a result of which some instruction can be allowed to execute in parallel. Inherit means getting the features from someone else. Suppose I'm the father, my son got the features of me, that is inherited from me, and I got inherited features from my father. In the same way, my son got the inherited features from me, and so on, our process will go on. So inherit property of a sequence of instructions, as a result of which some instructions are allowed to execute in parallel. That is, more than one instructions are executed to allowed in parallel. Why? Because inherent property of a sequence of instructions. Note that this definition includes parallelism across a sequence of instructions. This could be a loop, conditional, or some other valid sequence of statements. There is the upper bound where we can apply the parallelism. Then what is ILP? Dependencies within a sequence of instructions determine how much ILP is present. To what degree we can rearrange the instructions without compromising the correctness. Hence, our aim is to improve the performance by exploiting the ILP. That is our main aim, or that is our main target, to improve the performance by exploiting the ILP, that is instruction level parallelism. How do we exploit? Have a collection of transformations that operate on or across program blocks, either producing faster code or executing more ILP. Recall from before, an optimizing compiler does this by iteratively applying a series of transformations. Our transformation should rearrange the code from the data available statically at the compile time and from our knowledge of the underlying idea. Now, what is the key idea? These transformations do one of the following. Either it can expose the more ILP, or it can perform a rearrangement of the instructions. Then loop level parallelism and dependency. We will look at the two techniques, that is software pipelining and the static loop unrolling, that can be used to detect and expose more loop level parallelism. Now, what is a loop level parallelism? ILP that exists as a result of iterating a loop. That is known as a loop level parallelism. Now, there are two types of dependencies that is available. One is loop carried or one is loop independent. A dependency which only applies if a loop is iterated, that is known as loop carried. That depends on the loop. Whenever a loop is applied, or whenever which one applied if a loop is iterated. That whenever a loop is iterated, that is known as a loop carried dependency. Next is your loop independent. That is, it does not depend on the loop by which It can perform the operations, it can do the operations, that is, it will dependent on the body of the loop itself, that is within one iteration. So loop carry applies if a loop is iterative, and the next dependency, that is loop independent, depends on the body of the loop itself, that is within one iteration. This is the example. This is the for loop. For I equals to 0, I is less than equals to 100, I plus plus. I plus 1 equals to AI plus CI. Then x1, this is your pi plus 1 equals to pi plus ai1 plus 1. That is your s2, this is your loop independent dependency. Note that we know that ai plus 1 refers to the same location. So these are the dependent on the, not independent on the one another. This is the next example. This is two loop carry dependency. We will make use of these concepts when we talk about software pipelining and loop unrolling. Now, what are typical transformations? In detail, high level, low level, as I told you again. So this is also done. 3 topics are done. Now, 4th topic is local transformations and loops. What is local transformation? The transformation which operates on the basic blocks or extended basic blocks. That is the first block, that is the basic block. That transformation is known as the local transformation. Our transformation should rearrange the code from data available statically at the compile time and from knowledge of the underlying hardware. That is the transformation that should be rearrange the code from the data at the compile time and from knowledge of the underlying hardware. What are the key ideas? This transformation do one of the following while preserving the correctness. Means what is the use of transformation? How they are performing while preventing or preserving or continuing the correctness. Expose more ILP, such as later transformation in the compile time and can exploit this exposure. Perform a rearrangement of instructions which results in increased performance that is measured by execution time or some other metric of interest. So what are the local transformation that operates on the inner loop or the basic loop or the extended basic loop, that is known as the local transformation, that is used to rearrange the code from the data at compile time and from knowledge of the underlying hardware. We will look at two local optimization that is applicable to loops. One is static loop unrolling, that is loop unrolling replaces the body of a loop with several copies of the loop body. That is, with the use of loop unrolling, we can replace the body of the loop with different unlooping so that looping can be done effectively with the help of ILP, that is thus exposing more ILP, that is more than one instructions are executing in parallel. Key idea is that reduce the loop control overhead and thus increase the performance. That is, reduces the control overhead, reduces the resources, reduces the amount, reduces the money, and increases the performance of the program. That is your main output or main target. Then, what is the software pipelining? It reschedules the instruction from a sequence of loop iterations to increase or enhance ability to exploit more IAP. That is the software pipelining. That is rescheduling the instructions from a different iteration from a sequence of loop instructions to increase the ability or to increase the performance of the program. Then what is the key idea? That is reduce the store due to data dependencies. So there is a comparison between the static loop unrolling and the software pipelining. So loop unrolling replaces the body within the loop that by making the different copies of the loop body, thus exposing the IAP, that is instruction level looping. on instruction level parallelism. These two are usually complementary in the sense that scheduling of software pipeline instructions usually applies loop unrolling. That is, the scheduling is generally used to apply loop unrolling during some earlier transformation to expose more ILP, exposing more potential candidates to be moved across various different iteration or different looping of the or different branches of the loop. Now, what is static loop unrolling? Observation. A high proportion of loop instructions executed are loop management instructions. That is a high proportion, that is a high category of the loop instructions executed are the loop management instruction. Next example should give a clear picture on the induction variable. Key idea is eliminating the overhead could potentially significantly increases the performance of the loop. This is the example. We will use the following loop as an example. This is the example, C example, that starts with the 1000 and decrement one by one and end with the 0. It is greater than 0, not equal to 0. That is, it ends with the 1. So it's starting with 1000 and ends with the 1. That is 1000, 999, 998, 997, 996. Then curly braces open, uses xi equals to xi plus constant. That is, if I am using xi, first of all it is 1000, that is equals to x 1000 plus constant. Then again, and then next iteration will follow. Then the I value is 999, that is 999 plus constant. Then 998, that is 998 plus constant. Then 997, that is 997 plus constant. 996, that is 996 plus constant. 995, that is 995 plus constant. In the same way, it will go until the I value becomes the 1. That is at 999 times it will execute. Now, what is static loop unrolling continue? A trial version to the MIPS. Our example translates into the MIPS assembly code below without any scheduling. Note that the loop dependence in the loop, that is xi on xj. So this is your xi on xj. That is xi on xi. That is more than one loops are dependent on one another. This value, it depends on this value. If this value is not arrived, this is not arrived. So the output of this, it depends on this. At the next iteration, it also depends on the output. This is the parallelism on that one output or the one variable is dependent on the another variable. Then this is loop LD F00 R1 F0 array element ADD F4 F0 F2. That is add the scalar in the F2. Then SP DADD BNE, that is branching the loop using the registers. Now next slide is static loop unrolling continued. Let us assume the following latency for our core pipeline. First of all, FP ALU operation. Another FP ALU operation. The latency in CC is 3. Then FP ALU operation store double. That is instruction using the result. That is producing the result. That is using the result. CC is your clock cycle. Then FP ALU OP store double, that contains the latency in clock pulse cycle, that is 2. Then load double FP ALU OP, that is 1. Then load double store double equals to 0. Also assume that functional also assume that functional units are fully pipelined or replicated, such as one instruction can issue out every clock cycle. That is assuming it is not waiting on a result. That is, it is not waiting on a result. It performs the operation, gives the output, and the next iteration will follow. And the next iteration again follow the instruction, do the output, perform the output, and give the result. Assume that no structure hazard exists as a result of the previous assumption. Then this is static loop unrolling continued, issuing R instructions. Let us issue the MIPS sequence of instructions obtained. That is the MIPS instructions or sequence, that is clock cycle issued. This is looping, that is LT FOOR1, that is at the FOOR1 the clock pulse side issued is 1. Then there is a stalling, that is a waiting purpose, that is uses the clock cycle, that is 2. Then next is your add, performing the add operation at D, then using the functions or using the variable, that is F4, F0, F2, and the clock pulse cycle used is 3. Then store, the clock pulse cycle is 4. Store, the clock cycle is 5. Then SD F40 R1, the clock pulse cycle or the clock cycle issued is 7. Then store, again wait for a moment, the clock cycle is 8. B and E, performing the next operation, that is binary exponent, then using the R1 and the R2 as the register, and also using the looping part, and the clock cycle that is used is 9. And then also there is a stalling, that is a stoppage or for a moment, then the clock cycle is used is 10. This says we can push S and D after B and B if we alter the offset. Each iteration of the loop takes 10 cycles. These are the 10 cycles. We can improve the performance by rearranging the instructions in the next slide. We can push SD after B and E if we alter the offset. We can push ADD UI between the LT and the ADD D since R1 is not used anywhere within the loop body. This is the, here is the reschedule loop, that is the same schedule is, or the same loop is rescheduled. That is clock per cycle here is used, now 6, that reduces the or increases the performance, reduces the cycles. This is the best we can achieve because of the inherent dependency and pipeline dependency. This is the looping, that is LT, uses the function, uses the operation, uses the register, and use only the one clock cycle, that is 1. Then performing the operation at the second cycle only, performing the next operation, that is add, then wait for a moment, that is store, then uses the BNE operation where we can increment or decrement the values. Then there is a SD operation where we can offset the values of the SD. Observe that 3 out of the 6 cycles per loop iteration are due to the loop overhead. That is your next part. Hence, if we decrease the loop management overhead, we can increase the performance. So if we decrease the number of overheads, number of cycles, then we can improve or increase the performance. The solution is that static loop the solution, how we can perform or how we can increase the performance by using the static loop unrolling. Make n number of loop body, adjusting the loop terminating conditions and perhaps remaining registers. This results in less loop management overhead since we effectively merge n iterations into one. This exposes more ILP since it allows instructions from different iterations to be scheduled together. This is issuing the instructions, that is the unload loop on the unroll loop from the running program with an unroll factor of n equals to 4 will then be loop, that is LD, ADD, SD, LD, ADD, SD, LD, ADD. So at each iteration where LD is performed, and then addition is performed, then sum is performed. Then again LD is performed, addition is performed, SD is performed. Again SD, LD, AD. In the same way, at last DADD is performed. This is n loop board is 4, n equals to 4. That takes iteration as a 4, a number equals to as a 4. This is LD, KDD, SD, LD, LD, LD. This is adjusted loop overhead, that is SD and DADD. Note that the renamed registers, this is the renamed register. This eliminates dependency between each of our loop bodies of different iterations. Note the adjustment for the store and the load offsets only store the highlighted. Now let us schedule the unrolled loop on our pipelining. This is the scheduling that contains or that takes 13 clock cycles. 4 are used for LDs, 4 are used for ADs, that is ADD, 2 are used for SP, 1 is used for DADD UI, 1 is used for SD, and 1 is used for BS. Let us schedule the unrolled looping or a pipeline. That is the next example, that is the how to schedule on the pipeline. This takes 14 cycles, that is from 1 to 13, that is 14 cycles for one iteration of the unrolled loop. Therefore, with respect to original looping, we now have 14 by 4, that is equals to 3.5 cycles per iteration. Previously 6 was the best we could do. So now it becomes 3.5, from 6 to 3.5. So it increases the performance of the program. So that program efficiency will be increased, program performance will be increased. We gain an increase in performance at the expense of extra code and the higher register and usage pressure. However, loop unrolling has significant complications and disadvantages. Now, what is unrolling? What are the limitations of the loop unrolling? Unrolling with the unroll factor of n increases the code size by n. It might present a problem. Imagine unrolling a loop with factor n equals to 4, that is executing a 4 number of times, that is a multiple 4. Then what are the limitations? One would need to provide a copy of the original loop and the unrolled loop. Increases the code size and the management, increases the overhead. There might be a problem of the upper bound on the reduction variable. More firmly, the original copy should be included, that is the number of iteration is not a multiple of the unrolled number. However, loop unrolling has some significant complications. We usually also need to perform register renaming to reduce the dependency within the unrolled loop. Then next is your software pipeline. Now let's see with the help of book what we have covered in this topic, that is unrolling or software unrolling or loop unrolling. This is a diagram, or this is the unlock root by factor of 2. This is the example that we give with the help of PPTs. This is the diagrammatically shows how it will perform. That is CPE performance for different degrees of loop unrolling. Only integer addition and multiplication improved by the loop unrolling. That is double, float, integer. That is unrolling factor k. This is the graphical representation of the inner loop. These are the multiple parts, that is load, multiply, load, multiply, addition, comparison, JG. That is for jumping to the greater part. Then abstracting operations on a data flow. This is the abstracting operation, the same operations, that is loading the operations, multiply, again loading, multiply, compare the operations. This is your data flow representation of combined pipe operating on a vector of length n. Even though the loop has been controlled by a factor of 2, there are still n multiply operations along the critical path. Then enhancing the parallelism, that is how parallelism can be improved. That is the next topic that we will discuss after the break. So first of all, let's take 5 to 10 minutes break, then come back and starting with the next topic. So let's take 5 to 10 minutes break. Now let's start with the next topic, that is software pipelining. So now let's start with the next topic, that is your software pipelining. As I discussed earlier also, what is pipelining, how we can use the pipelining. Software pipelining is an optimization method that can improve the loop execution performance of any system that allows ILP, that is instruction level parallelism, including VLIW and superscalar architecture. It derives its performance gain by filling the delays within each iteration of the loop body with instructions from different iterations of that same loop. That is, it derives the performance by gaining the different multiple parts within the iteration. That is, with the help of pipelining, we can do or we can perform multiple tasks simultaneously. That is, more than one iteration can be used in any system. This method requires fewer registers per loop iteration than loop unrolling. So that requires less number of registers per looping or per iteration than the loop unrolling. This method also requires some extra code to fill pre-header. Pre-header means that is beyond the or that is pre to the header, and drain the post-header. Or fill means inserting the elements pre-header and drain the software pipeline loop, that is post-header. We will see in the next example. Key idea. What is the key idea? Why we are using this? The idea is to increase the performance by scheduling the instructions from different iterations into a single iteration. This is the example. Consider the instruction sequence from below. This is loop, this is LD, F00, RI, F0 equals to array element, add scalar in the F2, that is adding the F2 to the F0, that is adding, then SD, F40, then stores the result, DADD that is decrement the PTR or decrement the pointer, that is R1 hash minus 8, then B and E, that is branching the instruction or branch execution, that is R1, R2 loop, branch if R is less than or equals to or not equals to R2. So branch the conditions if R1 is not equals to R2. That is LD, ADD, SD, DADD, UI and branching. Then which was executing in the following sequence on our pipelining, that is loop, LD, ADD, SD, DADD, UI, BNE, that is branching. LD is again using the register 1, that is at F00 location. This is F00, that is the array element. Then this is at the first clock cycle. Then there is a store, means there is some pause. Then that is at the next cycle. Then ADD, F4, F0, F2 at the third iteration. Then store 4, store 5, SD, F4, 0, R1, that is at register 1 at the 6th location at the 6th clock cycle. Then DADD UI, that is for decrementing the values. Then BNE, that is branching the execution. This is the diagram. This is the diagram that shows a pipelining diagram for the execution sequence is given by LD. First of all, each write instruction is a number or a no operation, that is NOP, no operation, that is a store. So each red color, there is a store, that is no operation, that is NOP. There is a LD, then ADD, addition operation, SD, then decrementing the value and branching the instruction. So these lines or these red lines show the no operation. We could be performing useful instructions here. Now, software pipelining eliminates NOP by inserting the instructions on different iterations of the same loop body. So this says insert the instructions from different iterations to replaces the no. So a software pipelining eliminates the various operations or various NOP by inserting the instructions from the different iterations of the same loop body. So this is LD, this is ADD, SD, DADD, UI, BND, that is branch. How it is done or how is this done? First of all, unloop the loop body with the unroll factor of n. That is, unroll the loop body with the unroll factor of n. We will take an n equals to 3 for example. For example, take the n as a 3. In this example only, select order of instructions from different iterations to pipeline. Then paste the instructions from different iteration into a new pipeline by running the example repeated below with software pipeline. That is, this is the diagram that is used for running, for pasting the instruction. So I have taken the value, I have taken the n value as a, or the unroll factor as a 3. Then select order of the instructions from different iterations to the pipeline. So the loop is first of all LD, that is first one is LD, then F00 R1, that is F0 equals to array element, then add the scalar in the F2. This is the scalar element, so add the scalar element in the F2, then ST, that is stores the result, then DADDUI R1 for decrementing the pointers, then BNE, that is branching if R1 is not equals to R2. So this is the same concept. So this is how we can unroll or how we can unroll the looping by simply using the unroll factor, that is n. For example, 3. Select the order of instructions from different iterations to the pipelining, paste the instructions into the new pipelining and run the example with the software pipelining. So loop is first of all LD, then ADD, SD, DADD, DUI, BNE, that is branching. Now consider the instruction sequence from below or before. First one is your LD only, F00, array element, ADD, same, add scalar in F2, store the result, decrement the pointer, branch if R1 is not equals to R2, which was executing in the following sequence in our pipeline. So this is executing at the first stage, store 3, store, F40, 6, R1 7, then again store, that is there is some exhaust or there is some jumping or there is some movement, then R1 R2 loop, that is at the 9th location, then there is a store, that is at the 10th location. So first of all there is a LD, then there is a addition operation, there is a SD operation and DADD UI, and there is a branching operation. Now, step 1 is unroll the loop body with the unroll factor of n. We will take 3 for our example. We will take 3. This is iteration 1. So this takes 3 iterations. Iteration 1 plus I plus 1, iteration I plus 2. Note, we are unrolling the loop body, hence no loop overhead instructions are shown. There are 3 iterations or 3 looping that will be collapsed into a single loop for containing instructions from the different iterations of the original loop body. So this is LD, F00, R1, ADD, F4, F0, F2, then there is a SP. So this is your first iteration, that is this thing, SP is the first iteration, then again I plus 1, LD, F00, R1, again same values, F4, F0, F2, again same, F40, R1, again next iteration is I plus 2, taking the LD as F00, then addition operation, then SD, F0, F40, that is R1. So there are three iterations. As we are unrolling the factor, or we have taken the unroll factor as a 3, so n equals to 3 for this example only. Now, what is the step 2? First of all, take the unroll the loop body, then select the order of instruction from different iterations to the pipeline. So there are again selecting the order of operations. But how we can order, or how we can select the order of operations? We will select the following or operation for the pipeline loop. This is the SD, that is F40R1, then add F4, F0, F2, then LD, F00R1. So we have taken three iterations, that is I plus 1, I plus 2. We use the pipeline loop, LDD, LAD, addition, subtraction, so that we can ensure that no instruction will be collapsed into a single pipeline loop. Now, what is the step 3? Paste the instructions from the different iterations into the new pipeline loop body. That is pasting the instructions from the different iterations that is available for iterations, that is iteration 1, iteration 2, iteration 3, into a new pipeline loop body, that is a new figure of the pipeline. That is, first of all SD, then ADD, LD. So this is your first iteration, looping, then ADD, next, then LD. So take the three operations, put into the new pipeline, and then perform the two operations, that is DADDUI and DND. So you take the one operation or one action or one instruction from iteration 1, that is SD. Take the next instruction from the iteration 2, that is ADD. Take the next instruction from the iteration 3, that is LD, and then using the new pipeline, use the operation or use the pipeline procedure, that is DADDUI, and then branching. Now we just insert a loop, pre-header and post-header, and the pipeline loop is finished. This is pre-header and this is the pipeline loop body. There is a post-header also. So pre-header is instructions to fill the software pipeline. Pipeline loop body is loop. This is SD F416. So this is the pre-header, that is before the loop body. Then there is a SD, that is F416 at register 1, that is stored in MI. Then ADD D, that is F4, F0, F2, that is MI-1. Then again LD F00, that is taken in MI-2. Again DADDUI R1 R1 hash -8. Then there is a branching. Branching contains three parts, R1, R2, and looping. Again there is a post header, that is instructions to drain the software pipeline. This is the looping part, SD, ADD, LD, DADD, UI, branching. Assuming that we reschedule the last two instruction steps, our pipeline or our pipeline loop can run in 5 cycles per iteration, that is in a steady state, which is better than the initial running time of 6 cycles per second. So if I am using this one, it is so better for using the 2 iterations, for using the 5 cycles iteration, which is better than the initial running time, that is of 6 cycles per iteration, but less than the 3.5 cycle that is achieved with the loop unrolling. So this is the main advantage. What is the advantage of loop unrolling? It increases the performance of the program, that is program performance, and it also increases or reduces the number of cycles that is used for the loop unrolling, that is cycles per iteration. Next part says unrolling pipelining can be thought of a symbolic loop unrolling, which is analog to the executing Tommasolo algorithm in software. So loop unrolling is very important feature that is used with the pipelining for ensuring that program performance will be increased, and whenever there is a program performance, whenever there is a flow, so we can increase the program performance and perform the operations. Now, there is a comparison between the software pipeline and the loop unrolling. How we can compare? Comparison. Consider the application or consider the parallelism in terms of overlap instruction versus the time curve that is scheduled using loop unrolling. These are the legends. This is used for single iteration of the unrolled loop. This is the number of overlap instructions due to the iteration startup and the overhead. This is the legend that is used as a single iteration. Overlap between the successive iterations of the unloop loop. And there is a timing part also. Then there is a single iteration of the unrolled loop body running at the peak or running at the loop or running at the pipeline. Next point says the unrolled loop does not run at the maximum overlap due to entry and exit overhead associated with each iteration of the unrolled loop. Then a loop with the unroll factor of n and m iterations will occur or incur m by n non-profit cost. So these are the loop unrolling. Now, what is software pipelining? In contrast, software pipelining only incurs a penalty during startup, that is pre-header or filling, and then there is a drain, that is a post-header. So pipelining incurs a penalty during the startup phase. That is the startup phase, this is the drain phase. Except for the startup and the drain, the loop runs at the maximum overlap. Next point is the pipeline loop body also incurs non-maximum overlap. That is the maximum part or the non-maximum, that is the minimum part overlap the pipeline loop body that incurs during the startup, that is your fill operation, as well as the drain. Since pipelining instructions are executing or different from iteration to iteration and thus maximize the stalls arising dependency between the different iterations of the pipeline loop. So that's all for today's session. Now let's see with the help of a book what we have covered in this topic. Next topic is your enhancing parallelism. At this point, our function have hit the bound imposed by the latency of the arithmetic unit. As we have noted, however, the function units performing addition and multiplication are fully pipelined, meaning that they can start new operations every clock cycle. So at every clock cycle, it must be performed or it must be executing at the different stage. So it must be executing or performing the loop unrolling with the help of the parallelism, that is instruction level parallelism, that is ILP. We cannot compute a new value for the ACC until the preceding computation has completed. Even though the function unit can start a new operation every clock cycle, it will start one cycle per second or one every cycle in the L unit, where L is the latency of the combining unit, or where L is the latency period where the latency can be performed on the operation. We will now investigate what are the sequence method or what are the method that is available for latency. So there is a parallelism is multiple accumulator, that is more than one AC, that is more than one accumulator are used at the same time. That is for a combining operation, this is associative and the cumulative, such as integer, addition or multiplication. That is we can perform at the same time on an accumulator with the help of ALU, addition operation, multiplication operation, division operation. So these are the syntax, how it is denoted. This is combine 4, combine 5, combine 6. This is combine 6. This is the diagram that shows the CP performance or the CP performance for the K loop or KV loop. This is the same diagram or the same function that is used. One is for load, one is used for MUL multiply, one is again used for load, multiply, addition, comparison, then JG, that is jump, that is greater than. Then this is a combined 6 data flow that represents how data will be flowed. As I told you the example, n-1, I-1, I-2, latency time, that is cycles per element. Then reassociation or reassociation transformation, that is how we can reassociate the elements and transform into the multiple parts. This is our syntax, or this is a function, that is combine 4, combine 3, page number. This is the comparison of the multiple functions. This is a CPE, that is cycles per element performance of the for the K loop unrolling with the reassociator. This is the diagram that represents how data will be flowed in the with the help of data flow graph. This is the data flow diagram of the combined 7. There is a practice problem. This is also a practice problem. Now, 10th is summary of result for optimizing the code. Till now we have covered multiple topics like modern processor, optimizing the compiler. Today I've covered pipelining, what are the methods to improve performance or optimize the code. Now, let's take a summary of the result for the optimizing the combining code. Our effort is to maximize the performance of a routine. As I told you, our main target to increase or maximize the performance of the program that adds or multiplies the element of a vector has clearly paid off. The following summarizes the result we obtain with the scalar code not making use of the SIMD parallelism provided by the SHE vector instruction. So we can use or we can afford the element by comparing the elements with the use of SIMD instructions or parallelism. This is combine 1, page number, then function, page number, method, integer, floating point. Then by using multiple optimization, we have been able to achieve a CPE close to the 1.00 for our combination. For our combination of data type and operation using the C code. This is the SIMD code, this is the unrolling code or throughput bound. So that's all for today's session. Now, if you have any doubts, then please text the doubt and I will answer you. But before that, let's take a quick review what we have covered in the today's class. So thank you so much everyone. Let's take a quick review what we have covered in the today's class. We have started with the 4 topics, or we have started with the 4 topics in this chapter, that is introduction, pipeline scheduling, instruction level parallelism, local optimization, and loop, that is unrolling the loop. So first of all, introduction. What is the scheduling? That is rearranging or ordering of the program execution to improve the performance of the program without affecting the accuracy or the correctness. We have discussed about multiple ways and what are the or how does software based scheduling is different from the hardware based scheduling. There are 2 types of scheduling, one is software based, one is hardware based, and how it will be different from one part to the another. We can afford to perform more detailed analysis of the instruction sequence. We can generate more information about the instruction sequence and thus involves more factors in optimizing the results. But there is a significant factor where we can enhance the increases. We have seen how to increase, how to implement the scheduling, or how different scheduling, that is software and hardware scheduling, are different for each other. These are the architecture which we have discussed. There are three phases. One is middle end, one is front end, and one is back end. There is a compile time optimization that are subject to many predictable and unpredictable factors. These are the predictable and unpredictable factors. Now, what are the two types of optimization? One is high level optimization and one is low level optimization. We will focus on low level optimization. That is what we have talked about in the today's class. Then first part is finished. Next part is scheduling. That is state branch prediction. We have discussed about this. There are two approaches. One is direction approach and one is profile based prediction. Now, what is direction based prediction? That is prediction taken or not taken. This is usually 40% of the average that you have taken the prediction. This is the diagram, how to use the prediction, how to fill a branch delay slope, score sequence, and it's the graph. Then profile based prediction, one is direction based, one is profile based. Collect the profile information at the runtime. Since branches are bimodal, that is highly biased, a more accurate prediction can be made based on the collected information. Then next part is your instruction level parallelism and dependency. That is how one instruction or how more than one instructions are executing at the same time. That is your ILP, instruction level parallelism. That is inherent property of a sequence of instructions as a result of which instruction can be allowed to execute in parallel. Now, note that definition implies parallelism across a sequence of instructions, that is in blocks, that can be used for conditional operations. We have discussed about the multiple branches. Then how one instruction depend on the another instruction, that is your dependency. Hence, improve the performance by exploiting the ILPs. Before we are using, that is optimizing, the compiler does this by iteratively applying a series of transformations. A transformation should rearrange the code from data availability at the compile time or at the runtime. Then what are the transformations? What are the key ideas? Expose more ILP much that the later transformation can exploit the exposure of the LP. Then what is loop level parallelism? That is ILP that exists as a result of the iterating a loop is known as the loop level parallelism. There are two types of dependency. One is loop carried and one is loop independent. This is the example we have discussed. Then next is your local optimization and loops. That is your local transformations or optimizations and loops. We have discussed about the transformation, what are the key ideas. Then we have discussed about the two local optimization. One is static loop unrolling and one is software pipeline. Now, discuss one by one. One is static loop unrolling. That is whenever we unroll the loop, then that is whenever we decrement or manage the loop instruction, that is your static loop unrolling. This is the example. This is the example we have discussed about this. This is also example we have discussed how to issue the instructions, how we can push the instructions one after the another. Then solution is your static loop unrolling, how to increase the performance and decrease the overhead. This results in less loop management overhead since we effectively merge an iteration into one. This is the example we have discussed about the looping, LDs, ADD, SD, ADD. These are the looping bodies, that is it will iterate 4 times. Let us schedule the loop unroll. This takes 14 cycles for one iteration. Then we have continued with the example. We have discussed the example. Now next part is your Software pipelining. We have discussed about the software pipelining. That is, what is software pipelining, how we will execute, how it will allow the ILP or the VLIWD, how it delivers the information. We have discussed about the pre-header, that is fill, and the post-header, that is range, and what is NOP, that is no operations, how different no operations can be used as storing the instructions, how it is written. This is the example we have discussed. There are multiple stages or multiple steps how we can perform the operations of the pipelining. That is step 1, step 2, step 3. One is pre-header, one is loop boarding, and one is post-header. There is a loop unrolling we have discussed, or comparison between the software pipelining and the loop unrolling. So that's all for today's session. Now, if you have any doubts, then please text the doubts and I will answer you. In tomorrow's class or in Monday's class, that is next class, I'm covering what are the limitations factors that is available in the program flow or that hindrance or that hindrance for the program performance. So let's stop over here. In the tomorrow's class, in the next class, we will discuss about the next topic. So now, if you have any doubts, then please text the doubts and I will answer you. Thanks a lot everyone for listening to me. Thank you so much.